Thank you very much for the kind introduction. I hope you can all see the slides and hear me okay. So on the first slide, you see already two of the main strands, two of the main topics of tonight. On the left-hand side, you can see ore. So this is a hematitic iron oxide ore, and we will discuss how you can reduce it more efficiently and with less consumption of production of CO2. And on the right-hand side, you see metallic scrap, and we will see what we can do with it. So we work on these sustainability topics in a large group, and I list my colleagues and friends here, and I will highlight their specific contributions a bit more in detail as we go along. And I should also emphasize that we have very nice collaboration and nice discussions with Professor Mark Willinger at ETH in Zurich and Professor Johannes Schenk in Leoben, who also help us in this field a lot. So the key question is right away, how can we tame kind of about 2 billion tons of metals produced every year? So this little sketch just shows roughly the immense magnitude of these amounts of metals that we are dealing with every year. And it becomes clear from such a visual how much energy and CO2 that might consume. So when we sum that up and handshake here to the questions that you just have answered, we talk about 8% of the global energy consumption per year that is used for the production of metals, and about 3 billion tons of ores, and not even including all the byproducts and the debris and the waste that you produce, just the pure ores that you consume. And by that, you produce about a third of all the industrial greenhouse gas emissions. So these are really, really gigantic numbers, quite obviously. And that makes this topic also scientifically quite interesting, because any even very tiny scientific progress you can achieve can potentially, of course, have a huge effect, a huge impact on that field. And that makes it really worthwhile to study, I think. Now, this is a little quote that I took from the blog of Bill Gates. And he writes, whenever I hear an idea for what we can do to keep global warming in check, I always ask, what's your plan for steel? So let's try to give Mr. Gates a couple of answers as we go along. So as I've already emphasized, the one thing is the sheer immense gigantic magnitude of the steel that is produced. So we had last year about 1.8 billion tons of steel produced, and the forecast for 2050 is 2.8 billion tons of steel production. And the key problem is obviously that most of that reduction from the iron oxide goes through the boudoir reaction and uses carbon monoxide, so carbon-based carriers, to reduce it. And that means you have this, through to this mass balance, a huge amount of CO2 emissions that coming about every year. And this demand is really drastically growing every year very rapidly. There are even scenarios currently underway under calculation which forecast that the steel demand and the concrete demand likewise might even more drastically increase than we currently assume, due to the efforts in protecting our coastlines against the rising sea level. Of course, due to global warming. And this is already underway, as you see here in Rotterdam, London, and Venice, and many other cities and places come into the same scenario. And when that happens, the amount of steel and concrete you use will explode. It will be huge. And so there are different scenarios where this all comes together. Now, and on top of that, we of course have a gigantic global market related to materials. It's just not always so easily recognized, because materials often are hiding behind the actual products, of course. When you think of your mobile phone or car or power plant, then materials have been key drivers for this. So the market is gigantic. And the question is, can this market be turned into a more circular and a sustainable one? And from the Max Planck research perspective, of course, the key question is, what are the basic research questions coming along with that? So the awareness for climate change is currently reflected by basic research that's drastically growing every year. When you just look at the number of documents, of publications here taken from Scopus, which are published in the field of climate change, then you can see that we talk about like 40,000 papers every year reflecting the immense importance of this topic. When you, however, look for the sources from which, for instance, the greenhouse gases are essentially coming, like here sustainable metallurgy, and you just have seen the numbers a minute ago, then the research, the basic research that is then reflected by corresponding publications is surprisingly modest. The same applies for other topics like scrap recycling, which is a source of up to 1/3 of all metals that can be produced, can in principle be covered by scrap recycling. But the number of publications are really small. It's really small in this field. That means the good news for a basic researcher is, of course, there's so much headroom for doing more research in this field because it's a really pretty empty space. The other important thing that I would like to highlight is sustainability needs a close handshake with experts from topics such as life cycle assessment. Sustainability needs quantification because just claiming that a certain product or process is more sustainable compared to another can be very misleading, and you need really mathematically exact quantification tools, and they exist, and I later talk a little bit more about them. And that includes really the entire product cycle, coming from the raw materials, obviously, all through the waste that it creates. And we will see that, of course, in much more detail. Let me stay for a moment with classical steel and iron making. So that's how it is done, like 80% nowadays of all the steel produced on the planet. So you collect the iron ore, get your carbon carriers, which is typically coal. You put that to sinter, respectively coke plants, and put it in a blast furnace. That is a mass-produced way of making the raw iron, and then you put it in a carbon oxygen converter. And the basic idea is that in the blast furnace, you have so much carbon through the coke as a reduction means that you have, when you tap the iron here, very, very high carbon content. That means you take all the carbon in the blast furnace and take all the carbon again out in this oxygen converter. So it's really a weird situation. And this is just a little snapshot without going into much detail here, that you just get a rough flavor how such life cycle assessments must be organized. So you just look here at the simple case of just the iron making part of such huge, operations. And you have the coke plant, the sinter plant, the blast furnace, and so on, as you just saw it, just to arrive at an iron or steel product. And then you have all these connections and all these mass and energy balance items that you must quantify. And what is very important and also a certain obstacle to make all this sustainability business in the metal sector more transparent is that most companies or branches or sectors try to define their own little niches where, of course, their respective products or processes look very good. And that has to do with the fact of where you place your different borders. So where do you start counting? Where do you end counting? So where are the gates and how are they quantified? And again, this is the same story. There are real experts who do this for a living, but it is not so easy from an academic standpoint to get through to the industry practice, because as I said before, not every company or branch has an interest of making these things entirely transparent, depending on in which part of the niche they're sitting. Another very important aspect is what we refer to as unintended consequences of an otherwise purposeful action. What that means is that sometimes the pressure to come up with sustainable solutions in the metals sector or the associated energy conversion sector is so high that not always very smart decisions are made. And I think we must also quantify the sustainability of these technologies. This is just an example where you see the blades of windmills, which are just used as landfill. And that is, of course, not the deeper idea. The same applies for something like used solar cell modules that which are, by the way, in part full of precious metals, silver, contacts, copper, and so on, not just the silicon from the absorber part. And so the key message is here that in all these materials-related sustainability technologies, we must also apply the same principle. This includes also, like Antje Boetius had already reported in her first presentation in this series, that this includes also the UN rules for sustainability, which are taken much broader than just looking for greenhouse gas emission and energy. It includes also illegal labor conditions, destructive mining, or the rapidly growing deep sea mining, for instance. As we learned from Antje last time, we have not much knowledge yet about the deep sea, but we start mining in it. So that cannot be the target to get hands, for instance, on cobalt or manganese or nickel. But this is already on the way. So let me stay for a moment with mining these ores, which is, of course, a big topic of its own. We have a big field in metallurgy that we call urban mining, and that comes from getting the metals obviously back from the waste. When you look at particularly at precious metals, where the prices are very high, you have about 5 grams of gold in a ton of ore. So that is a standard value that you get, for instance, from a good mine in South Africa. Now, when in contrast, you go to the WE, the so-called waste of electrical and electronic equipment, then you can have a much higher fraction of platinum group metals or gold or silver that you can retrieve. And there's a lot of chemistry and physics involved in these processes. They are on the way, but the total retrieval rate, the recycling rate, even of these extremely expensive metals, is still relatively low. Interestingly, that has often to do with the way how these precious metals are used in very fine nanoscales within these products that you see here. So we throw away about worth 50 billion euros of electrical waste every year on the planet. And most of that, interestingly, does not end up in recycling companies, but it ends up as landfill. And when you look at the recycling rates, and all these data pertaining to recycling rates must be read with a grain of salt. You must be very careful when you use such numbers, because they vary very drastically depending on from which branch or company or sector they come from. So they must be really interrogated and best be retrieved from published and quality controlled publications. But when you take, for example, copper. Copper is one of the key elements, and it's very limited metal available from ores. Copper is a key element for the electrification. That is a key driver for the higher sustainability of our industry and society. And yet, less than a third of the copper is actually retrieved and recycled. And that is a very low value. So one of the research directions must for sure be getting much more of these precious and rare materials simply back from the urban waste, from the post-consumer waste, from the things that we are throwing away. And that is in part not yet really done. So I come back to some of these recycling rates later. Let me jump back to the real huge groups that I mentioned before, particularly steel and aluminum, but also nickel and titanium, through their sheer quantity, being big players, obviously. I already emphasized the energy and greenhouse gas emissions, but what is also interesting when you look at the material that is scrapped already during manufacturing. So the table I showed before refers often to the post-consumer scrap recycling rate, so to the things that we in industry throw away where it's already mixed. But a very important source to tap high quality scrap is, of course, when it has not yet been mixed. And particularly in aluminum and titanium production, this scrap in manufacturing this amount is very high. Now you could, of course, say, let's do much more additive manufacturing. Most of you know that topic, and it's an absolutely fascinating topic. We also work in this field in the Max Planck Institute. But the total quantity that you can produce by these shape optimized and mass minimized design approaches is still very small compared to the mass production that is done in the sheet rolling and casting branches. So the total mass that you produce by additive manufacturing or can produce is relatively small, because the advantages of additive manufacturing indeed lie more in small series and not in big series. Also, you have a sustainability issue with the powders themselves, because they are aging through oxidation when you use them a couple of times. So sustainability when it comes to material science can be discussed in terms or along 2 directions. One is what we call the direct effects, and these refer to primary process conditions. So to improvement in the metallurgical and synthesis processes. An example is where you use hydrogen instead of carbon as a reductant agent when you, for instance, reduce ores. And I show a lot about this later. The second aspect is what we call indirect sustainability. is when you achieve sustainability improvement through the use of certain metal or materials products. Examples are magnets for electrification for an electrical engine, or high-strength aluminum or steels for making your car lighter. So one word about indirect sustainability. This is a nice example that I've taken from the textbook of Mike Ashby, and it shows a typical production cycle from some primary energy carrier all the way through to some production site. And in all these intermediate steps, you have key materials which are responsible for the efficiency of each of these steps. So in the primary sector, that can be, depending on your source of energy, can be corrosion or hydrogen resistant alloys. In a different type of sources, that would be, of course, different. A very huge amount of energy, as you all know, is lost in the energy conversion in the power plants. So where you need better high temperature alloys according to the Carnot efficiency, you need maybe hydrogen resistant alloys when you start using hydrogen as a fuel and so on, or thermoelectrics when you want to gain waste heat back, which is a huge problem, a huge source of loss in the industry and so on. Then you need, of course, strong and lightweight resistors and conductors for bringing the electrical current from A to B. Then you need magnetic devices in the transformers and in electrical engines, of course. And finally, in your processes, you need low tribology and high-strength alloys, stiff alloys, and so on. And you need, for all of them, longevity. That means they should stay in the process as long as they can, because the best sustainability recipe is still to have long-lasting materials that do not corrode so quickly. And you see, when you add up all these efficiencies, then you can get an impression from the role of the indirect sustainability of materials research, which can contribute to all of these individual steps. And again, the energy conversion is one of the most exciting sectors where efficiency increases can lead to really much, much better sustainability. Now, another rather busy slide, apologize for that, but what I want to show by this is just the, say, sector-specific emission of carbon dioxide equivalents, so the greenhouse gases. What you see here is that, and this is a target that we have to reach according to the Paris Protocol. But what you can learn from this slide is then we think of household, transport, industry, and the energy sector, that all these are areas where the materials that we're using and that we are inventing and that we are improving have a very big leverage, a very big influence. And that's, again, good news. Not only the environmental burden of these materials are very high when we produce and use them, but they can also, in their indirect benefit, help a lot to improve the sustainability in these huge sectors. That means, again, here the leverage of good action is very, very high. Let me give a very simple textbook example here, how these two effects can come together on a transportation item like a SUV, like a heavy car. So a very classical design here, like with a mass of 1.7 tons or so, would use a lot of steel traditionally because of cost and strength reasons. And now you can start off replacing some of that steel, for instance, by a high-strength aluminum material, or likewise by high-strength steels. That's not the main point here, by a higher strength affordable material, and by that reduce the weight of the car and hence the fuel consumption. Now, when you think a little bit further, then you could also say, let me make sure that these materials that I use here have come from sustainable sources. Let's stay for a moment with aluminum, which, when it comes from classical primary synthesis, is a very energy-intense material. But when you gain it from scrap, as we will see later during the talk, you save a lot of primary energy because the melting point of aluminum is very low. So you don't need much energy with 660 degrees centigrade to melt it. That means when you melt aluminum for a car from scraps, you have a very sustainable product, essentially. And then you can up these two contributions, the indirect effect, like the weight reduction here, plus the greenhouse gas saving, into a total product estimate. And that shows you how I think these type of rationales and ideas can enter actual real product design. Just to give you a flavor about the role of high-strength alloys, what they have achieved meanwhile, if you would build the Eiffel Tower again, it would only require 75% less steel for exactly the same design than when it was built first in 1887. So that is just a little milestone of how strong materials have become. Now, when you put some of these thoughts together and see how material science can contribute to a circular economy, you see many of these trends which are really interesting. So smart, intelligent, and efficient production pathways. Then materials for the entire chain of electrification. Likewise, all the materials for as sustainability enablers, from advanced solar cell absorbers to all the materials you have in windmills, power transport, and power plants, and so on. And then, of course, the longevity. That means the research on corrosion protection at high temperature against hydrogen embrittlement, and so on. These are absolutely key drivers for a higher sustainability in our field. Another rather new topic is the design for materials for what we call infinite recycling. That means every atom in principle can be collected and recycled. And that means you must upfront build this genetics of recyclability into the design of alloys. That is a new idea how we make materials. And then the biggest fraction, what I've outlined in the beginning, is the primary synthesis, because in all of these aspects, we must recall that you cannot cover the entire demand globally only from remelting scrap. That is not possible. You have in average about 30-35% that you can cover from recycling, but the demand and the growth of demand is so immense that you always need primary resources. This is very important to keep in mind. I tried to put this here into a certain axis framework to estimate, which measures are really very high in their leverage and which are maybe not so high, and which are close to higher technology readiness and which are more far from an application. So what I've already said, one of the biggest players is always corrosion protection and longevity. Just again, to give you a little feeling, not just the Eiffel Tower, but also the Brooklyn Bridge, which is actually older than the Eiffel Tower. It's a steel bridge, is still in use. And that means 70% of the steel that was ever made is still in use, mainly through their use in buildings, obviously. And so that is very important to keep that factor in mind. And then the electrical energy from renewable sources. So this is a rapidly evolving field. And that's why it's so interesting to really look around how all the synthesis and manufacturing in the metallic sector can be rendered to tap more of this green electrical energy. And then we have other aspects, of course, like the huge field of catalysts and their role they play for chemical production. Less scrap production during manufacturing, that's very important, has also to do a lot with the economical strings attached. And then we have a couple of aspects that I'm not going to tap too much into today because they are either not so much on the basic research side or the leverage is low. What is for us very interesting are the aspects here on the right-hand corner, where we talk essentially about really CO2 reduced primary production methods, and including also ideas that are simply not yet on the market. So where we simply entirely have to reinvent some of the methods how we make metals. That includes also things like plasma-based reduction, which is also a CO2 reduced production, but I show you later more details about it. So it's pretty far away from practice, but I think it has a very high leverage when it works. Or the idea that I mentioned before, how to build recycling features already into the material before you design it. And then we have other aspects that I'm not going to discuss in more detail. From our interest and perspective of research in the Max Planck Institute, these aspects on the right upper corner are of very high interest because they have a high leverage, a high scientific risk, a high gain to it. And there's a lot of basic research that can be done. Let me look a little bit closer into the real bad guy, into the coke plant and blast furnace, which stand alone, just these two instruments stand alone for about 6% of the global CO2 production. So that is really one of the real big guys to talk about. So we take a lump of ore, like shown here, the typical hematite, which is Fe2O3, and want to see from a thermodynamics perspective how you turn this into pure iron. So the minimum embodied energy, the thermodynamic energy, is about 6 megajoules per kilogram of this material. So that's when you think of like the metal in terms of a metal oxide battery, that's what you can win and must put in, can win and so on. That's the embodied energy from this oxidation process. Now, when you actually look the total energy, sum it up that you need in a real process to make the same kilogram of iron, you see that the efficiency is much, much smaller than this 100%. It's about 22 to 33%, depending on the processes and details. That means we pump much more energy into the production than we would thermodynamically need. So that is, of course, not really a surprise, but the loss of waste heat in these processes is really immense, because many of these processes are high temperature processes, like in energy conversion in power plants. And that is also often overlooked, that a lot can be improved here in terms of waste heat recovery. And by the way, steel is already very, very good in this field. When you look at steel with its like 22 to 33%, depending on the exact process, even aluminum is already much worse. And look at the other metals, which are even much more worse compared to the production of aluminum and of steel. But this is just to show you that as we typically deal with high temperature process, there's so much to gain in terms of conservation of the heat waste. So let's look a little bit closer at the reduction of the CO2 emission. When you just take a white scrap of paper and say, essentially look into the so-called Ellingham diagram, which is just collecting the competing thermodynamic processes, you talk chemically about a simple redox reaction. That means you want to take the oxygen out of the oxide or similar type of ionic structure, and you have to, in other ways, use for that a reductant agent. And that means you can efficiently use the carbon. That is the standard globally, why we produce so much CO2. I mentioned that on one of my first slides. But you can, of course, take also many other types of carbon carriers. So that means you can also use methane or even ammonia or other products. Ammonia, of course, is not a carbon carrier, but a hydrogen carrier. You can even use pure hydrogen or similar chemical ingredients that contain a lot of hydrogen. So you can use all kinds of crossover molecules among these. And you can use techniques like electrons directly, like in the electrolysis, or you can use the forced state of matter, you can use a plasma. And again, the plasma, of course, can operate with very different gas environments. So when you put all these chemical players and all the different types of excited structures that you can choose here on a table, you have a broad variety of techniques that you might want to revisit how they can be combined. And this applies also to the raw materials. When you see the complexity of possible ores and the scraps that you can use, you can come up with many, many different combinations which deserve closer research. Let me look at one in a little bit more detail. That is a so-called direct reduction. And that means you expose solid oxide, so a piece of ore if you want, to a reductant gas. And in our case, we have chosen not the typical methane or carbon monoxide like in a blast furnace, that would be carbon monoxide, but we use hydrogen. And this is a basic idea that is shown here in this overview that you have seen before. We tried now this route that's called direct reduction to go from the ore through a simple reactor in which you have solid ores or pellets that are made from ores and expose them to the reactant hydrogen. And then you produce something that is called sponge, so something like a very porous iron, and that is something you would put in an electric arc furnace to melt it down. And I come back also to that furnace. Now we have done this here in the laboratory with a nice collaboration with a couple of colleagues I mentioned in the beginning. And we just look here in a furnace at 700 degrees centigrade, how quickly such a piece of hematite iron ore is reduced when you use hydrogen. And you see here the reduction degree plotted as a function of time, and here the derivative that shows you the reduction rate, so how quickly it goes against the reduction degree. And so when you arrive at 1, you would have pure iron. And you see that you go through different stages of the oxide. So you reduce it not directly, but go from hematite to magnetite, from magnetite to wüstite, which is FiO. And this stage, as you see here, is a very, very sluggish one, a very slow one. So there's something you want to understand better. And here's a very nice online movie from our colleague and friend, Professor Mark Willinger, also a former Max Planck colleague from the Fritz Haber. And he did a very nice in situ experiment where he put a little piece of such an ore pellet into an electron microscope, which he then flooded in a defined way with hydrogen. And look what happens. You see here this rough and coarse surface of this iron ore. And then during the reduction, as the hydrogen-based reduction goes on, if I play this again, you see that this iron is then starting to cover the oxide beneath it. And when you now translate this into a simple schematic, as is shown here, you have here the wüstheit, the last oxidation stage that you need to reduce into pure iron. And this is, of course, here this ionic lattice. And as you have a gradient in the so-called chemical potential, the oxygen from here to here, the oxygen leaves that wüstheit, that oxide, and diffuses through this newly and freshly formed layer of bulk iron to the outside, where it would recombine with the hydrogen to form water. So the only debris gas here is water. And here you create the iron. However, when this iron layer is growing, the transport of the oxygen through that layer looks very difficult because it's a rate dominating process. The same applies, which is also not yet so well understood, to the question how these nuclei are formed. When not yet any iron is present, how nuclei form of iron atoms inside the wüstheit when you have taken the first oxide atoms out. So all these basic questions are not well understood and are currently under research. Now let us fly a little bit through such a pellet, which is a product that is made from the ore. It's just baked together to carry an oven load. And when you cut it open, this is all work by my colleagues Jan Ma and Isnaldi Filho and a couple of other colleagues who work on that topic. And you subject it to electron microscopy probing, you see that this is a very nanoporous, a very fine structure. It looks, by the way, similar if you do that with a single crystal of wüstheit. That means although the single crystal has such a high mass loss of oxygen and several phase transformation stages between these oxides before they finally turn into iron, that you have a very complex array of porosity, nanoporosity, and fracture. And you can put these boundary conditions from the electron microscope now into what we call a boundary condition treatment, a simulation. That is done by my colleagues Yang Bai and Java Mianrudi, who runs a group on sustainability, metallurgy, and the corresponding theory behind it. And then you can try to calculate how these reactions proceed through such a complex network and can directly couple this to experiments. This is still all in an early state in the making, just to give you a flavor of how we try to get deeper to the roots of the rate determining steps in these complex processes. And this is, for instance, analysis that Jan Ma, my colleague, made regarding the evolution of the nanoporosity as a function of the reduction time, to really understand where is the free volume, where can the water recombine, where can it form, where is it maybe recondensing, or do you maybe form water bubbles that lead to fracture and so on. There are many questions that are totally unclear. Where is actually the oxygen going to? How is the hydrogen penetrating a certain bulk oxide and so on? This is just a very messy slide. I know this. This is from Isnaldi Filho's work, where he very nicely, through the microscope, saw what kind of complex cosmos of defects, damage, interfaces, but also free volume you form when you have, for instance, here a little portion of pure iron that is inside the wüstheit, which is the oxide, and you see how through the phase transformation, a lot of mechanical stress is built up and fracture takes place and so on. And of course, through the loss of oxygen, you build up also diffusive porosity. So it's a real complex universe that you want to understand in detail. And we can even go a little bit deeper. We can go to the atomic scale if we have to, through the atom probe tomography group of my colleague, Professor Baptiste Go. And then this is a measurement by Seho Kim and Ayman El Sokka, where they look into the atomic state of these oxides. Here you see it before the reduction. Very unexciting. You just see these dots of iron oxide. Everything is fine as it is. And after the reduction, you see the pure iron. But what they discovered is that you have all kinds of very fine nano oxides that seem to remain in the material and don't get removed, don't get reduced. And that for sure has also an influence on the overall kinetics. So I switch gears now to a slightly different process. Think of a world where we just can't forget all these intermediate steps, which are either so energy consuming or which are so rich in the CO2 production and so on. And if we could directly go from the ore or some product from the ore, like fine ores, directly into this electric arc furnace. Why that? I show you in a minute why we would want to do that. And by that, you could reduce the entire process of steelmaking to essentially one simple furnace. So this is how these things look like. They actually exist. They are pretty big. They can have 100, 120 tons of weight. And you see these gigantic electrodes. They are typically graphite electrodes, and they are sinking into this huge melting pot, essentially. Why we have them all over the globe distributed is from companies that are specialized on making steel from scrap. As you saw in the beginning, steel is actually doing very good in the scrap recycling, and particularly the so-called corrosion-resistant stainless steels. So the steels that you know from exhaust pipes, from your kitchen, and from all the corrosion-resistant parts in the chemical industry. So these are very expensive steels. They contain elements like chromium and nickel and so on, so which you want to retrieve from the scrap. And that's why this technology of melting scrap through these electrodes, through a plasma, is quite established. And it's big fun. When you ever have the possibility to get close to these ovens, it's the best experience of your life. It's kind of noisy, but it's really cool. Now, we mimic this process in our laboratory. Of course, not in this big size, but as this technique in principle exists in large quantities, we modify it. That is one project in our institute where we work with a couple of colleagues together. And what we do here, however, we don't use the furnace in the same setup, but we expose it to a mixture of argon, just an inert gas, which is not doing too much, except enabling some recombination in the plasma, and 10% hydrogen. And we create a plasma from this through the electrical energy that comes through these electrodes. And then you can, in a very well-defined setting and sequence of melts, expose that ore to the plasma, ignite the plasma, start melting it, and then you do not only reduce in the liquid state the oxide, and the melting point of that oxide is not much higher than the iron, so you work in a similar ballpark, but you also lose some of the oxygen already through the vapor pressure. So it's a very, very efficient process, and we currently start to look only scratch at the surface. And here you see some examples of the first experiments from Isnaidi Filho again, where you see how after several minutes of exposure of the material to this type of plasma, of mixed plasma, you get pure iron. And this is just a fly-through, as you see here, the complex array. This is just after 2 minutes of plasma exposure with only 10% plasma. You can, of course, try all different kinds of plasmas, obviously. And you see these beautiful structures that remind us a little bit of some art from Miro, for instance. You see here this big particle of iron, which has been formed splashy-wise amongst this wüstite. And that was just stopped in between after 2 minutes. And then when you go on with that, you get pure iron. And that is a very, very interesting process because you don't put all the carbon in, which you later have to take out again and so on, and you get relatively pure iron. And again, here we zoom into the atomic scale. And we again expose these samples that are partially reduced to the atom probe. You see here on the left-hand side, atoms pertaining to the wüstite, that's the oxide. And again, these little dots are atoms. So we really go to the atomic detail here. And on the right-hand side, you see the freshly reduced iron. So you really see an interface here of this moving boundary from that plasma reduction. And you see, interestingly, now you can start to explore what the role of certain gangue elements are. So what are tramp elements? Because these ores in their natural habitat come with what we call gangue elements. They can have silicon, manganese, sodium, and so on, many types of elements. And you want to study how they influence the process, how they influence the kinetics, the chemical reaction, or the final product. So you're just opening a big box, a big gate into which nobody has ever stepped. And we do this really also down to the atomic scale. So let me, in the last few minutes, leave the steel part. And I apologize that I spent so much time on steel because simply the leverage of steel production is so incredibly high. But aluminum is very exciting too. Let me just remind you of this simple thermodynamic fact that we talk in the primary production, which is done by electrolysis, of 45 kilowatt hours per kilogram of metal produced for aluminum, because the bonding between aluminum and oxygen is so incredibly strong. So the enthalpy is so high. The secondary production, that means remelting it from scraps, is, however, comes at very low cost because the melting point of aluminum is with 660 degree low. So there are many, many strings attached, however. So there is not so much scrap on the market that you can produce all aluminum from it. That's for aluminum also about 1/3 that you can cover. But this portion you should cover. The scrap sorting is not trivial. There's a lot of engineering and science and even machine learning behind it to separate the scraps and so on. But a very important point is when you do an analysis of how you produce your aluminum, like I said in the very beginning, you must do it based on a very careful life cycle analysis. It's very often said that, for instance, all the primary synthesis of aluminum is very bad because you do it by electrolysis, but this is entirely incorrect, because when the electrolysis runs, for instance, totally on sustainable energy, it's perfectly fine. You just have to deal with the byproducts or with the electrodes, which are graphite and so on. So you must really look into the detail of a life cycle assessment, which aspect of something like an aluminum can production is really sustainable and which is not. The punchline, however, is of course that a high recycling content is always beneficial. One very important point about aluminum alloys to keep in mind is that they are very, very sensitive. That means you cannot easily mix them. And that is a real burden associated with aluminum. It's so nice to melt them, but when you mix them, you poison them mutually. So for instance, to give you a feeling, many cast products like huge engines and so on are very high in silicon. Or the alloys that you have when you fly in a plane that keep you safe are very high in copper content. Or when you take the post-consumer mixed scrap, which is very important to retrieve, but very hard to retrieve, are very, very high in iron, because they are mixed with iron scrap, they are connected to pieces of iron and so on, and they get iron content from the cutting of the pieces. And all these different alloy groups you can typically not readily mix. And so this is a little, again, an atomistic measurement done by the atom probe, just a little atomic fly through a little piece of an aluminum alloy, just to give you a feeling how many elements are meanwhile through the scrap recycling accumulated in a piece, in principle, a piece of packaging foil that you have at home around your chocolate. You would be surprised how many atoms are protecting your chocolate from being eaten up by you. So they are, like in a typical foil, you can find easily 18 different type of tramp elements that come from the scrap that are not needed for this process or for the alloy, just accumulate by scrap. And the art is here to find out which tramp elements can you tolerate, which tramp elements can you not tolerate, which, for instance, worsen the corrosion behavior, which elements lead to damage, to fatigue damage of a plane part that is obviously no-go, and so on. So you must really understand in detail what we call tramp element sensitive alloy design. And a last point that I wanted to make is maybe we simply have too many materials. Maybe we have too many elements used in products. This is a very nice diagram where you see the use of chemical elements in products coming from windmills, through cars, through modern sustainability technology, where you meanwhile use a third of the periodic element in one single product. Imagine what that means. And that makes it so hard to retrieve the scrap and use it. And this applies also to the metallic sector. That's a recent paper of Iso George, where he nicely compiled how we have turned also from the use of dominant elements like copper in bronzes, or in steels, it's obviously iron and so on, nowadays to a multitude of very complex alloys. They are on the one hand very exciting when it comes to properties and in terms of physical phenomena. On the other hand, however, they are not always very pertinent when it comes to sustainability, because they are very hard to be separated or in part use very expensive elements. Another avenue is when you just remember the simple and plain statement that mass and energy in these materials, of course, have to be conserved. Hence is the number of atoms that you have in such a sample are conserved. But many of the features that lend the material its properties are due to what we call the microstructure. These are interfaces, second phases, nanoparticles, dislocation, and so on. And these are not conserved. That means they can be rejuvenated, they can be modified and refreshed, they can be brushed up by the processing. Just take this little fly through to a simple little part like a screw. And you can see many of these features that lighten up that are really responsible for some of its mechanical properties. And they are not conserved by mass and energy, because there are things like interfaces, like nanoparticles, like dislocation, and so on. That means there's a lot of opportunity that can be tapped by modifying these defects in the material, and not only the chemistry. Let me show this in this diagram. And don't worry, I'm nearly done. It's one of my last slides, and then I stop. But This diagram, which I really like, shows the tensile strengths of aluminium alloys and for some of the biggest aluminium grades. And here I plotted the different main alloying elements. So here it's manganese, for instance, in your drinking can, or in your car. Aluminum, it's magnesium and silicon are the main alloying elements that you put into the aluminum, in which you then are not allowed to mix and so on. In your plane, you have additionally copper. In your mobile phone, you have zinc, magnesium, and copper, and so on. And you see an overall trend in the increase in the strength as a function of this chemical composition. Okay, so we seem to need that modification through chemistry. But you see also the scatter bars and properties here, particularly for the high strength alloys that are so important to reduce the weight of a plane or of a car or a ship. And here you see indeed that this scatter bar is gigantic, and that is not just a stochastic scatter bar, but that comes from the way how you produce a material, how you insert these microstructures. And that means we can come to an approach simply where you modify the alloys not only through their chemistry, but also through this processing microstructure, because this quantity is not conserved. So with that, as promised, I stop here. I thank you very much for attending the presentation today. I hope I could, blend some of the spirit into the audience, how exciting and how new this topic is. And this last slide, I did a boring summary here now, but this last slide I've chosen to show you that also from many other research and science field, there are interesting facets that play into this field of research. And with that, I stop here and thank you very much.